All right, the second section of 2.1 deals with a measure of position that's really commonly used in statistics called z-scores. These are actually used even more than percentiles and quartiles. So to introduce it, let's look at an example. Macy, a 3-year-old female, is 100 centimeters tall. Her brother is 12 years old and is 158 centimeters tall. Obviously, Brody is taller than Macy, but who's taller relatively speaking? That is, relative to other kids of the same ages and gender, who's taller? According to Center for Disease Control and Prevention, the heights of 3-year-old females has a mean of 94 and a standard deviation of 3. And for boys, it's 190, 149 and standard deviation of 8. So they're both taller than the average. But who's taller relative? So one way to compare measures from different distributions is to see how many standard deviations each is away from the mean. These are called z-scores. So we don't really, I'm going to introduce the formulas down here, but you don't really need the formulas. Macy's 100 centimeters tall. The mean is 94. She is 6 centimeters taller than the mean. So then to scale it, how many standard deviations is it? Well, 6 divided by 3 is 2 standard deviations. That's what z-scores are. It's a measure of how many standard deviations she is above or below the mean. In this case, she's 2 standard deviations above. But to use the formula, it is right here. If you have sample data or population data, it doesn't matter. So the z-score for Macy would be her height minus the mean divided by the standard deviation. She's 100 centimeters tall minus the mean, which is 94, divided by the standard deviation of 3, which is exactly the calculation we just did. So she's positive 2.0 standard deviations above the mean. The way we interpret this is we just say Macy is 2 standard deviations above the mean for her age group and gender. So let's do it for Brody, see how many standard deviations above the mean he is. Brody was, 158 minus 149 over, 149 and then 8. That is 9 over 8. And we usually put these in as decimals. That's 1 and 1/8, so it's 1.125. So Brody is 1.1 standard deviations above the mean, but his sister is 2 standard deviations above the mean. So that means Macy is taller relative to her comparison group than Brody is relative to his, because she's more standard deviations above the mean. Now you can get negative z-scores. If you were to get a negative z-score, that just means you're 1.4 standard deviations below the mean. That means you're below average, which isn't a bad thing, of course. But you're under the average, I should just say. Okay. All right. So again, why is this useful? It's useful to compare measures from different distributions. Trying to compare apples and oranges, right? So to the right is the table that displays 3 of the top 4 home run performances in the history of the Major League Baseball. So from this display, who should be regarded as the greatest hitter of all time? Well, Babe Ruth hit 60 and 27, Maris 61 and 61, and Bonds hit 73 in 2001. So, hard to argue. Barry Bonds is the best performance. He hit the most. But, this is a 75-year difference. The game has changed a lot in 75 years. So, what was Babe Ruth's performance like relative to the people of his era compared to Barry Bonds? So, this table down here displays the mean and standard deviation of the number of home runs hit by players that averaged at least 3 plate appearances. So basically, players that were regulars. In 27, the average number of home runs per year was only 7.2, with a standard deviation of about 10. And when Barry Bonds was playing in 2001, they were hitting on average 21 home runs. So, why? Well, I don't know why. Probably technology, better bats, better balls, better diets, better weight programs, better training programs, steroids, right? The game is just different. So let's calculate each of these players' z-scores. The z-score for Babe Ruth. So, and the reason we calculate z-scores is so we can kind of have a measure of how they did relative to their era. So it's the performance, it's the x value minus the mean of that generation divided by 9.7. Type that in the calculator, we get 5.44. So this is pretty amazing. This is 5.44. So again, if they asked us to interpret the z-score, you'd say Babe Ruth's home run total was 5.44 standard deviations above the mean for his time era. That's that's amazing. A little later on in the year, we'll talk about how rare this is, but for right now, we'll just say it's rare. Roger Maris, 61 minus 18.8 over 13.2, 4, sorry. I typed that in already. 3.14, 3.15. So Roger Maris hit over 3 standard deviations above the mean, which is still pretty fantastic, but nothing compared to this. And Barry Bonds hit 73 home runs. However, people hit a lot more home runs in his era than, still an amazing performance. 3.91. But, whose performance was more rare? Whose performance was more phenomenal? Babe Ruth's performance in 1927 was really significantly, well, I shouldn't say significantly, was better. So my vote goes to the old timer. All right.